RAM is at its most useful when it has address decoders connected to it. These are just binary to selection line decoders. They allow you to control all of the different registers with a simple binary address. You can read from register 0, register 1, register 2, and register 3. Now, the way this is set up, I have different address decoders for the writing and the reading, which means that I can write to an address while looking at a different address. So, at register 3 currently has 1010 as its data. If I look at register 2, it's just blank. But I can look at register 3 while choosing to write to register 2. And I think register 2 is going to get, yeah, 0111. That's a good thing. This write control works by it keeps all of the lines high. It keeps all of the lines on all the time. So it's like 0 lines are selected. But then when I press a button, the torches over there turn off, and one of these lines goes cold and transmits an update, which causes the writing to happen. So let's check on register 2. See what it contains. What a surprise! It contains 0111. So this is an example of how addressed RAM works. RAM where you can access and control its different registers via binary addresses. Address decoders are essential for large bodies of RAM. This, for example, is 32 bytes. It would be nearly impossible to use 32 different wires to try to control each of the different registers. Therefore, I use an address decoder. This is a narrow decoder design, which I created recently. It's because when you're dealing with decoders can get pretty wide, and I realized that they tend to be wide, but not tall. And since the RAM is tall anyways, I realized, well, just don't waste space and use the tallness to contain the decoder. And that's what I've done here. This means that I'll be able to stack multiple units of this 32-byte array next to each other without wasting a lot of space on the decoders that have to fit in between. Now, something else about this design is that I've chosen to have the reading and writing controlled by the same address, by the same decoder. So, for example, if I want to read from register 3, currently nothing's in it, but when I write that nice test sequence in it, 101 1011, then you can see it appear right there. Because with this configuration, you're writing whatever you're looking at. Now, this seems like this will cost you some flexibility if you think about, well, wouldn't it be nice to be able to write to memory separately from where I'm reading? And yes, that is true. But for the use of storing large amounts of memory, it's actually rare that you'll ever want to read and write at the same time. If this is hooked up to a CPU and is used as its bulk memory storage, so if it's computing a bunch of data and just needs to shove it somewhere, and there's not enough room in all of its CPU registers, then it sends it to the RAM. And it just goes to the RAM. It's a write operation. The CPU doesn't need to read and write from the RAM at the same time. There are some kinds of memory where you will want to read and write at the same time, like these registers which I made for my CPU. In that case, I use separate address decoders for the. In fact, I use one for the A input, B input, and where I write the output. But here, I take a different approach. I sacrifice flexibility for compactness. And this is fairly compact. I think this is probably the most compact 32 bytes of memory you're ever going to see in Minecraft. Well, in vanilla Minecraft, that is. I plan on taking 8 of these units and wiring them together to create a 256 byte memory array. Why 256? Well, why that many, and why not less? The reason of not less is because, well, I wanted a big amount of memory. And the reason I stopped at 256 is because that 256 is controllable by 8 bits of addressing. 2 to the power of 8 is 256. So, an 8-bit CPU will be able to very easily control 256 addresses of memory. If I wanted to have more than 256 memory slots, or words of memory, or registers, or whatever, then I would need to do something like read 8 bits twice, in which case I could have 64 kilobytes. But 64 kilobytes won't fit anywhere. Trust me, don't try to make 64 kilobytes. You'll hurt yourself. And hurt others. Hurt people you care about. Unless you're really good. Like me. Okay, so that's pretty much where I am on my RAM projects. Oh, something else that you might notice about this RAM is the power supplies are only every other unit. To help illustrate this, I have a quad of RAM, or it's a 2 by 2 units of 2 by 2 size RAM. It's a 2 by 2 of 2 by 2, so 4 by 4. I don't know how to say that properly. But anyways, you can see that a single power supply, a single torch, can be the power supply for 4 different memory cells. And it works the same for memory reading as it does memory writing as memory reading. Now, it is possible to actually just get rid of these and use the power supply here as part of the insulation. So this means you use a little less insulation, and it means your power supplies run in the same direction as the register. But the reason I don't like doing that, though others do, I don't like doing it because that's not a trick you can apply to the lower power supply, and I like to keep things more even. So yes, 32 bytes. The biggest challenge, the reason I don't want to go have a single unit be longer than 32 bytes is because the number of repeaters involved. Access time is the most important feature in RAM. It's the most important time. It doesn't really matter how long it takes to write a value. What matters is how long it takes for you to get access to data which is stored. Here, it'll take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It'll take 11 ticks, so 1.1 seconds, from putting an address in here to getting the result. Well, that's the worst case time. Other times will be better, but if I double this to 64 units, then access time is going to jump to about 1.9 seconds, 2 seconds. It'll double. And that access time starts getting a little bit too slow. So 32 bytes in a single line is about as long as I want to do, because if I want to access my memory quickly. So my plan is I'll have wires running this way, which will then branch off to multiple units of these stacked side to side, like one here, and also have some branching off in the other direction. So it's going to be like this. And this central bus is going to contain the input lines for all input lines that connect to all the units, the output lines that connect to all the units, and the address lines that select the different units and select the registers within the units. This is going to be a mess of wiring. Well, hopefully not too much of a mess, but it's going to be a lot of wiring. This thing is going to be the biggest challenge in making the RAM. And it's just a structural challenge, which those are the challenges you start facing once you get into the higher levels of complexity. Knowing how to make a RAM cell is one thing. Knowing how to arrange it well into 32 bytes is a different sort of challenge. And then compactly addressing those 32 bytes, that's another challenge. And what I have to work on now is getting all of those chunks to work together as a single unit, so that at this point here, I'll be able to punch in an 8-bit address and have the data appear on the outputs right there. That's the goal for RAM. Get everything to come together into one single point. You can control it from a single point, and yeah, it brings everything together for central control. That is the purpose of RAM. Another problem which needs to be addressed is a problem which is particular to this kind of 2x2 footprint RAM. Well, and actually many kinds of 2x2 footprint RAM. And it's the question of, where do you put the repeaters? In a zigzag pattern like this for the input lines, you can't just put a repeater here, because if that line is receiving a signal, is receiving data, for one thing, the repeater up here blocks the piston and blocks it transmission of information to that piston. That piston can't see anything. Not only that, but you start contaminating the read line for the next register, or this register, or the next register. Anyways, you end up with signal contamination. So what you have to do is you put the repeaters, well, there are a number of things, but what I've done here is I've made a gap where there are no registers and put the repeaters there. So I have 8 registers which repeat in a space of 18 blocks. Normally, you'd be able to repeat it to do 8 registers every 16 blocks. But because of technical limitations with the zigzagging, 18 blocks is what you need to do. You can actually compress it to 17 blocks by having the flat wiring begin here and moving all of these down one, but I don't like it as much. It's actually aesthetic reasons, interestingly, funnily enough. But more important than the difficulty with the input lines, let's get rid of that lever, are the problems with the output lines. Redstone charge travels only 15 blocks from it, from its source. But if you look at how the power supplies are set up, there's already 1 unit of distance, 1 unit of wire here. 1 unit of distance is being spent just before you even arrive at the outputs. So data coming from the 8th register in an 8 register chunk, data coming from the 8th register won't reach the end. However, I did a little bit of cleverness and realized that even if it doesn't reach the end, what you can do is make it reach a block in front of a repeater. I could have tried putting a block here, and that would have worked. And there we go. Yeah, and that works. Except, suddenly you lose the ability to read from the first register. And a solution where you read from one register by sacrificing another is not a solution. So, what I did is I did a little zigzagging down here, like this, where dropping down and hitting this block allows the 8th register to receive, to transmit all the way to the repeater. But the wire up here means that it can also connect with the first register. They do it by different means. One, because this wire just goes directly on top of the block and powers it, and the other by the wire just barely touches the block and sends power into it. But both of them cooperate and don't interfere with each other, and allow this kind of output line to work to work with only needing a repeater every 8 registers. And to span the gap, you have to use another block here to get the extra distance. And this bit of wire isn't a problem, because even though that is extra distance that has to be covered, it's the same extra distance as this wire. They're both 1 block away from this, and so this piece of wire benefits from the same setup as the 8th register. It just barely reaches this point, it hits the block, and the next repeater gets it, and it continues along the line. So combining an added zigzag to the bottom of your registers for the output lines, combining that with inserting repeaters into the upper zigzag, doing those will allow you to stack your 8 register chunks every 18 blocks. And in that way, you can get large-scale structures of memory. Now, stacking sideways, however, is really easy. You can just add repeaters. Every 8 bits, you just add a repeater. It's very simple and straightforward. So you could just, put another 8 bits of this over here and have a 16, and have data that has 16-bit words, but I'm just sticking with 8-bit words for this device. Okay, that is how you go about using this RAM for larger scale structures.